Welcome everyone. In this video I'm going to continue my CH32 tutorial series, and I'm going to show you the implementation of a communication protocol with a certain temperature sensor. So far I covered most of the fundamental principles and peripherals of this microcontroller, so now I'm going to implement some more complex projects using this microcontroller, and for one of those projects I need to be able to communicate with this sensor. So this sensor is the DS1820B digital thermometer chip, and its unique feature is that it can communicate with the microcontroller using one single wire. Of course, it needs the power pins, VCC and ground, but then the communication between the microcontroller and the chip is realized through one single wire. And this temperature sensor is a simple semiconductor-based temperature sensor, so because of that it has a very narrow temperature range as compared to, for example, a K-type thermocouple. So it can measure between minus 55 degrees Celsius up to 125 degrees Celsius. And it has a rather okay accuracy, plus minus 0.5 degrees Celsius between minus 10 and plus 85 degrees Celsius. So if you have any kind of, let's say, automation project or some kind of temperature logging project around your house, then this is perfect for that, because it's perfect for example, monitoring temperature around the house or monitoring the temperature of water in a pond or something like that. And therefore it is used in many hobby projects, and you can find a lot of tutorials for Arduino and different microcontrollers, but I'm going to implement the communication protocol of this chip on this CH32 microcontroller. And in this tutorial I'm going to print the temperature values on the serial terminal, but as a teaser, in future projects this data will be transferred somewhere else. So as usual, I'm going to use this Moonriver Studio 2 as the developing environment, and all we have to do is we have to create a new project. So the microcontroller is the V003, and I'm using the F4P6 unit, and then this will be the 11th part of the tutorial series. So the project is done. Let's open the main.c, which is under the user folder. So as usual, I'm going to remove the garbage, which we don't need first. This one, we need the UART because we need some serial communication. And then we have a few lines, which we don't need here. And finally this one. So to ensure that we see communication, let's implement the usual printing. I provide some delay so I have time to open the serial terminal, and then we just print some text. And it compiles nicely, so far so good. I haven't removed anything unnecessary from the code. So as I said, the basic principle of this thermometer chip is that it can communicate with the microcontroller back and forth via one wire. So it can send and receive instructions through one single wire. And there is no clock signal, no chip select signal, nothing, just single wire. And for that, we have to set up a GPIO pin, which can do both. So let's create a function for that. So this will be our function. And you can see it has the chip name and then set pin mode, and it accepts one parameter. And that parameter will decide whether we use this pin that we implement in this function as an input or an output. I cannot use booleans in this environment, so I'm going to use an unsigned integer, and if I set it to 1, then that will mean that I want to use the pin as output, and if I set the integer to 0, then it means that I want to use it as an input. So let's create this structure that holds the, let's say, settings for the pin. So this is the structure that we are going to initialize, and if we look at this, then we can see that we can assign 3 different, let's say, parameters to it. One is the mode, the other is the pin, and then the third is the speed. So first, let's go with the pin, because we want to fix the GPIO pin. And then I will use PD2, because actually we don't have too many pins on this specific microcontroller, which doesn't have too many other additional functions. For example, PD1 I cannot use because the SWIO is connected to that pin, and I need it for the debugger and the programmer. And then PA1, for example, I cannot use PA1 because it is connected to the external crystal, which provides the clock. And then there are other pins assigned for the UART, as you can see, pin 5 and pin 6 on port D, and so on. So this is one of those pins which I can use as a pure GPIO. So let's assign GPIO pin 2. And then we can select the speed, and I just assign 50 MHz. It doesn't matter in this program. And now we have to write an if-else block to choose between output or input. So if the output value, the parameter that we pass to the function, is 1, we want to define the pin as an output. And then I do it like this, else if. So I block out anything else which is not 0. So then I can pick this. Probably not the best practice, but it will work just fine. So if the output is 1, then I have to define the mode as an open drain output. So the reason why I selected the output mode as open drain is the following. First of all, for the wire or the data line, we need a pull-up resistor of 4.7 kilo ohm, and the reason of using that pull-up resistor is that the resistor has to be able to pull up the signal pin to high level. And then why we do it like that is because the default state of the communication line is 1. And then what we want to do is that either with the microcontroller we want to pull it low, but when I release the line, it jumps back to high again, and the same should happen from the chip's perspective as well. So when the chip is clocking out data, then it pulls the line to low and then it releases it, so it jumps back to high. And this will be the distinction between 1 and 0 signals. And in order to allow this behavior, we have to define the GPIO pin as an open drain output. And then in the opposite case, the GPIO mode has to be a floating input because it is controlled by the chip. So it's a floating input on the microcontroller side, and then its state is controlled by the temperature sensor. So when the temperature sensor releases the communication line due to the pull-up resistor, it jumps high, and then the temperature sensor can also pull it to ground, and then the level of the signal on the chip will be 0. So that's why we have to set it to floating. And then we just pass this to the corresponding init function. And as I said, we want to define this on port D. So then together with this GPIO D and pin 2, this becomes PD2. And once again, we need a 4.7 kilo ohm pull-up resistor on this pin. So one pin of the resistor goes into the 3.3 volt power supply line, and then the other goes to this specific pin PD2. So now we can handle these pins, but we have to be able to start communicating with the chip. And this is the first timing chart which we have to study first. And we can see how we can send a reset pulse and receive a presense pulse from the chip. So by default, we are at VPU because we pulled up the pin to the supply voltage, which is 3.3 volts. And then how we send a pulse is that we pull it to ground. Here you can see that it goes low. And then for at least 480 microseconds, we hold the line at ground. And then we release the line. And in the meantime, we have to switch our still output pin into an input pin. And then the input pin, after 15 to 60 microseconds waiting time, has to detect a low value. And if we detect a low value between this time period, then it means that the chip showed its presence, so it basically sent back a 0 to the microcontroller. So if we have this sequence, so first we can send out a pulse with a certain width, and then we can detect a 0 signal within a certain time frame, then that means that we can actually communicate with the chip. So let's implement that. So we have our function here, and it will return an 8-bit integer because we have to later on use this bit to, for example, let the code to proceed or not. Because if there is no presence detected, then we of course don't want to progress with the rest of the code because we can't read anything out of it. So let's create a variable which we will use as a presence. And this will be just simply a 0 or 1 depending on whether we found the chip or not. And now we can use the function that we recently implemented. So that will be this, the setPinMode function. And we will set it as 1. So that means that this will be an output. And then, if you remember the timing chart that I just recently showed, then we have to pull down the output pin to ground. So we have to write the bit of the specific pin that we are using, which is the PD2. So we have this write bit function. We are on GPIO port, and we have GPIO pin number 2, and we want to pull it to ground, so the bit has to be reset. That's done. And then if we look at the timing chart again, we can see that this state has to be maintained for at least 480 microseconds. So let's do that by just simply introducing 480 microseconds delay. And that's that. And then we have to switch to another mode, which will be the input mode. So we have to release the line. And then, in order to release the line, we have to switch into the floating input mode. So how we do that is that we have the DS18 setPinMode, and we set it to 0, which will mean that it is now an input. And then we wait between 15 to 60 microseconds. I just wait, let's say 30. And then we have to read the input data bit on the specific pin that we use for this purpose, which is again GPIO pin 2 or PD2. And actually this bit can be passed to the presence variable. So we have this, and then I put an exclamation mark here, and I will explain why. But first I write this input data bit, and then we have GPIO and then GPIO pin 2. So just remember, if the chip is present, then it will pull down the signal line to low and hold it at that level for 60 to 240 microseconds. So when we read out the pin value at that specific time, it will show 0. But it doesn't make sense if the presence value is 0, because then in like interpretation it would mean that if it's 0 then it's false, so it's not present. So I just invert the output value. So if we found the chip, then the presence will store number 1, and if we don't find it, because the line is still high within that specified time frame, then this bit here would be 1, but the presence, when you try to interpret it, is 0 because it's not present, it is false. So yeah, I need to invert this output. And then the waiting time so far was 30 microseconds, and the chip's output pulse width is about 480 microseconds again. So 480 minus 30 is 450 if my math is working well. And simply we return the presence. And that's all. So now we can detect the presence of the chip. So to test this, I have my small setup. This is the temperature probe, as you can see. And then this is the ground wire of it. And then this is the VCC wire of it. And then here, the green wire is the output or input, depending on which communication stage we are at. So this is the wire, the communication wire, and here is a, not 4.7 because I could not find that, but a 3.3 kilo ohm resistor. And it's pulled up to 3.3 volts. So this is a supply line, and then it goes to PD2. So now we can pull up the serial terminal and run this code to see if we detect the chip. And of course we need to run this function. So what I'm going to do is the following. So then this will be the code. So we print a decimal, which will be the output of this function. So I compile this, and then I upload this and open the serial terminal and connect to the chip. And it prints presence equals 1. And this is already the inverted value. So the chip is there, which means that we can continue the development. So in the next step, we have to study the next timing chart, which is the read and write time slot diagram. And we can see on the top row that we have the master write 0 and master write 1 timing sequences. And then we have the master read 0 and master read 1 timing sequences. They look fairly similar and it's not super difficult to implement them, but let's see how to do that. So how to write the 0 is the following. As you can see, we have to pull down the wire to ground, and then we have to hold it at ground for this time interval. So it has to be at least 60 microseconds, but it has to be less than 120 microseconds. So in between this time interval, we have to set it to 0. And then we release the bus, so it jumps back to high. And then if we want to write a 1, then we pull it down, as you can see, but only for a short amount of time. And then we release the bus and let it be released, so be at a high value. And then this will indicate the chip that it is now a bit 1. And then we have the reading sequence, and that is fairly similar but not the same. And how we do it is that we pull down the signal pin to ground, and then we wait a little bit. We can see that we have a 15 microseconds window here. So we wait a bit here, and then we release the bus. And we wait again, and we have to see what will happen. Because if we release, and for example here where we have this sample, the gray block is still low, then it will read as 0. But if after the release we can see that the signal jumps back to high, so the block is at the part where the signal is getting high, so above the threshold level, then the sample bit will be read as 1. So depending on what we read on our floating pin, will determine whether we have 1 or 0 sent from the thermometer chip. So let's implement the reading first. So this is our function, and it will return an integer because this will be the bit that we read from the temperature sensor. So we need to store that bit somewhere. So we set it up like this. And then we have to set the pin mode to 1. And why we set it to 1? Because we want to use it as an output first. And then we have to pull down the wire to ground. So how we do that is very similar to the line here. So I just copy paste. So the GPIO D port and pin 2 is set to reset. So pulled it to low. And then we wait for 6 microseconds, because this is roughly halfway towards 15 microseconds. And then we switch the pin mode to 0. So now it's an input, and it's a floating input, and we wait another 6 microseconds to wait until the temperature sensor pin sets the line to either high by releasing it, or holding it to low by holding it at ground. And then we pass actually the value of the PD2 pin to this variable. So we have to read the input data bit, and it's on GPIO-D and pin 2. And then we have to wait a bit more, because actually the full pulse sequence is 60 microseconds long. So we already spent 12, so we wait 48 more microseconds. And then we just return the bit, something like this. So if we look at this function and the timing chart at the same time, then we can cross-correlate the two things. So here we set the pin up as an output, and then we pull it to ground. So far so good. And then we wait 6 microseconds, and then we release the line. So we set it to floating input, and then we wait again. And then we read the state of this pin, and then we wait again. And whatever was the value here in this line will be returned by this function. And now we know how to read a bit, so let's do the writing part. So the function will look like this. It doesn't return with anything, but on the other hand, it accepts a bit. So of course, because we want to write a bit, 0 or 1, so we have to pass it to the function as a parameter. We do it like this. So again, we look at the chart and we can see that we have to set the pin mode to output first. So let's do that. So that has to be 1. So now our pin mode is output, and we have to set the line to ground again. So I just do a copy paste, and then we need an if-else block. So if the bit we received is 1, then we do something, or if it's not 1, so bit equals 0, then we do something else. So if the bit 1, then we look at the timing chart and we can see that we have to wait a bit. So I wait 5 microseconds here, and then we have to release the line. So how we do that is that we set the pin mode to 0, and that will automatically allow the pull-up resistor to pull it back to high again. So that's how it will work. And then we wait out the rest of the pulse here. So that is 60 minus 5, so 55 microseconds. However, if the bit is 0, then we actually already at the ground. So we just have to wait 60 microseconds, so the full pulse width, and then we can release the line actually by setting it to floating input. And then I just wait for 1 microseconds just to, let's say, finalize the release. So once again, with the timing chart, how it works. Here we set the pin mode 1, so it's an output. And then I already wrote here that we pull it to ground here. And then if we want to write a bit 1, then how we do that is that we wait a little bit, and then we just release. So then it can be pulled up by the pull-up resistor. So actually it will be high, but we don't set it to high. We just let the pull-up resistor to set the line automatically to high. And then we just wait again until this 60 microseconds pulse width ends. And if we want to write 0, then since the pin is already 0, we just wait. And then we release, so we can send the next command if we want. And then we wait again just to let the thing settle. So it's that simple. And this is all nice, but these are just bits. And the chip communicates via bytes, so it expects to receive a byte, and we are expected to receive a byte or 2 bytes from it. So now we need to implement the functions which send and receive the bytes. So let's start with the write byte, and it will look like this. So it doesn't return anything because we are writing, but it accepts a byte parameter, so we can pass something to the function and that will be written on the chip. And then we just need a for loop which has 8 iterations. And then we just need to write the bits. So that is something like this. And what we do here is that we take the byte and then we use the AND operator with the 0x01 hex value. And what will that do is that it masks out the LSB. So everything in the byte will be set to 0 except the LSB. So for example, if we have this, then this will become this, because both cases we have 1 here. So this is fine so far. And then we take our byte and we shift it by 1 bit to the right. So then the next number here would be the 0, and then it would be the other 0, and then it would be the 1, and so on, which would be masked with this 1. And since we use the logical AND operation, it only returns 1 for the cases when both, let's say, numbers match. So if both numbers are 1, then the bit that we are writing is 1. So this masking and writing operation does that. So it sends 1 bit at a time from right to left. So this one first, and then this, and then this, and so on and so on. So this was simple. And then we have to read the byte, and this won't accept any parameter, but it will return a byte, obviously. So first we need the byte, which will be 0 in the beginning, and then we need another for loop, which will look like this. And then we do the shifting in the beginning, but in the first iteration it will have no effect. And then what we do here is the following. We have to check what is the bit that we first read. So if the read bit is 1, then we take the byte and then we use the logical OR operation and OR it together with the opposite of 0x01, which will be 0x80. So that is this. And what this does is the opposite of the writing operation. So then how this for loop works is the following. So in the first iteration, this have no effect because there is nothing in the byte variable yet, because it was initialized as 0. So then, if the first bit that we shifted out is 1, then we take our byte variable and then we use the logical OR operation with this value. So from left to right, we actually start to fill up the value of the byte. So let's imagine that we received 1. Then what will happen is that the byte will become this value. And then the program proceeds and goes to the next iteration where I equals 1. And then we shift this highlighted number to the right by 1 bit. So this would become 0, 1, and then the rest, because it's shifted. And then if the next bit is again 1, then actually it would become 1, 1, and then the rest is 0. And then this goes on and on until the for loop finishes the full byte. So that's how it is reconstructed. And then once the byte is done, then we just return it. So that's very simple. And now the function is ready. And then finally we can read the temperature out of the chip, because now we can send and read bits and bytes and whatever. So let's implement the actual reading, because the temperature reading will be also just 2 bytes. So since we are reading something, we have to return with something in this function. So we will return with a 16-bit integer, because the conversion values are 12-bit. So the closest number that we can use for that to store the 12-bit number is 16-bit. So that's what we are going to use. And first, as a safety, we have to check the presence of the chip. So that's what I'm going to do here. So we have an if here, and then we initialize it. And if it's 0, then we print an error message, which will look like this. And then we return with this expression. And I just missed the parentheses here, so let's fix it. And then we can start sending information to the chip. So let's test this write byte function. And then we write 0xcc, which is skipping the ROM. And then we can write another byte, which is the conversion of the temperature, 0x44. And then we set the pin mode to 0, which means that we are operating as an input, so the line is released and it will go to high. So now here we have to wait for the conversion, so I will just use a while here. And then we just read the bit from the PD2 pin. And while the conversion is not ready, then the code will stand here. And when the conversion is ready, we can jump out. And then the sensor is not returning the value immediately, but it reads it to its so-called scratchpad. And we have to read it from there. So what we have to do is that we have to initialize the chip again. And then we send the byte to it. So that will be write byte. And we again skip the ROM, so 0xcc. And then we want to read the scratchpad. So again, we write another byte and 0xbe, which means that we want to read the scratchpad. And when we send this instruction to the chip, then it will start returning the 2 bytes. So what we do here is that we create a variable for one of the bytes, which will be, for example, temporary LSB, and that's the first byte that is shifted out, and we just simply read it. And then I do the same, but that I will call MSB. So now we have 2 bytes returned from the thermometer chip. And we have to return with an intelligible value for the rest of the code. And that will be an integer, potentially signed. So that's why I'm not using uint 16. And this is a casting. So we cast the following value to this. So we have our MSB, and we have to shift it up to the upper part of this 16-bit variable. And then we have to combine it together with the LSB. And now from 2 8-bit numbers, we created the 16-bit number. And that's done. But the problem with this is that this will just return a simple number, which is just a raw data, and we don't know that in Celsius degrees. So let's do that as well. Let's do the conversion, and let's implement a function that does the conversion. So let's create a function that converts this integer into a floating point number. And then actually I'm going to use the same code that I just recently showed in the SPI related video, because as we know, we cannot just print a floating point number directly on the UART or serial terminal with this microcontroller. So we have to split up the floating point number into 2 integers and then print that integer in a tricky way, so it will look like as if it was a floating point number. But on the terminal, actually it doesn't matter because it's just a string of characters. So we use this kind of workaround to print a string of characters which looks like a floating point number. So first we need an integer, and I'm going to use a 32-bit integer, and I will call it scaled. And why scaled is because I scale up the raw data, so this, by 10, because I need to show at least 1 decimal digit. So to achieve that, I need a 10 times larger number. And then I have to divide it by the LSB, which is, in the case of using 12-bit resolution with this temperature sensor, is 16. It's in the datasheet, so you can check that. And if you are planning to use this device with another resolution, then you have to change this number accordingly. And then we have the wall part, which is nothing else than we just take the cast of the scaled and we divide it by 10. So far so good. And since we do this int casting, then we chop off everything behind the decimal dot. So this will be just the whole number of the conversion. And then if we want to have the fractional number, then we take this int, and then we take the absolute value here of the modulo 10 of the scaled number. And then you can see that we have a problem here with the compiler, because we need another library to be able to use this apps function. So we go up here, and we have this stdlib. And then we come back here and create our printf, which will actually print our number. So first we print a decimal, and that will be our wall part. And then we print a decimal point, and then we print another decimal with just 1 digit. And then I need the Celsius symbol, so degree C, and then a line break. So that's fine. So the first decimal, that was the wall, and then the second decimal, that was the fractional. And our output is ready. So we come to the while, and then we need a 16-bit integer, which will be our, let's say, raw value, and that is just to get temperature raw. So we need this because we want to print it. So I just print it as like this, so raw, and then the number, and then a line break, and this will be the freshly acquired raw value. And this will be just the 12-bit raw output. We need to convert it into temperature, and that is done by passing the raw to this function. And then we wait, let's say 1 second before we do another conversion. So I compile this, and then I send this to the microcontroller, and then we open the terminal. So now you can see that it's printing. So the value is 387, and that is equivalent to 24 degrees Celsius. It's quite nice. So if I touch the chip, that should return a higher number. And I can see that the terminal is falling apart because it's actually not really liking the encoding of the degree value. So I have to clear the terminal. And you can see that now it's 28. So now I'm holding it in my hand, and it warms up the metal jacket of this sensor. So the auto scroll is not the best in this built-in terminal, but you can see that it works. And it cooling down now because I released the sensor. So that's what you can see here. And basically that's that. So as you could see, it was fairly easy to set up a communication between the microcontroller and then this one-wire temperature sensor. So I will use this in a future project because I needed some, let's say, data source, and this seemed to be a cool project to implement. And if you want to know more about this chip, I really recommend you to visit my website because I explained everything about this chip. So if you don't like to follow the video, then you can read the same thing in your own pace, and then you can copy everything. And of course, I have a GitHub page. So if you want to get the full main.c file, just go to my GitHub and download it for free, and then you can tailor it to your own needs. And if you like this kind of tutorial series or my content in general, please consider becoming a channel member, because that can help me to spend more time on these kind of projects, so I can release source code for free for everyone, and then I can buy the newest gadgets and develop something useful with them. So I hope you found this video useful, I hope you learned something, and see you in the next video.